thank you very much for the introduction. And thanks also to the committee of this conference for inviting me to give this talk. I want to use this opportunity to introduce a vision for rebuilding the foundations of a subfield of business process management known as process mining. I will have a talk in 3 parts, like the matrix. The first part will be the world as it is, or as we think it is. That's process mining. In the second part, I'm going to talk about the infrastructure for rebuilding that world. And in the third part, I will talk about how this vision of rebuilding process mining can be achieved and some advances in this direction. So, process mining is a subfield of business process management which deals with uncovering knowledge about business processes starting from event logs. Event logs are simply sets of records of events that happen during the execution of a process. Like, for example, you are executing an order management process on top of an ERP system, such as SAP, and SAP will record everything that is happening in this process. Every single time somebody clicks to add some information into the order, to modify some information into the order, to approve some step in the order, to do some check, all that will be recorded, and this will lead to records of tasks that are being started, completed, suspended, restarted during the execution of that process. And given this humongous amount of data, process mining is a family of techniques that allows you, for example, to discover what is the process that is behind the process model. So you can derive from a log a process model. I don't think this is helping in this microphone. So we can derive a process model from the event log, or we can take an existing process model, because typically business analysts who work with business process models, they have lots of existing models of what they think is the business process, so that captures their belief about how the process should be executed. And given an event log and this input model produced by an analyst, we can test the conformance of the process with respect to the model. We can detect if the process is actually deviating with respect to what the business analysts believe it should be doing. So that will tell you whether the process conforms to the log or whether the process model does not conform, and in that case it will actually give you some diagnostics about how the reality deviates with respect to the model, or how the model deviates with respect to reality. Another subfamily of techniques in process mining is what I would call deviance mining. So here I now have 2 event logs. One event log for one variant of the process. That could be how we execute the process in Estonia. And another one is how we execute it in Latvia. Right? Or that could be, these are the good cases, the cases where the customer is satisfied, and this other log is the bad cases, the cases where the customer complains. And we want to compare these 2 sublogs in order to find what are the differences. What distinguishes the cases in the process where the customer is satisfied from the cases where the customer is not satisfied. And finally, another area of process mining deals with performance monitoring, understanding how the process is performing in terms of non-functional properties such as time, cost, and error rates, and so on. So I'm not going to touch on this one. I'm going to talk about these 3 areas of process mining, which are the ones that are going to be of interest in today's talk. Process discovery, conformance checking, and deviance mining. So let me start with discovery. The input of automated process discovery is a log, which we can see as a big table, initially not in first normal form, just like a huge table, where every row is a record, and importantly, there is a designated column that tells you what is the case identifier. So if this is an order management process, that will be the purchase order identifier, so that I can relate every event to one execution of the process. That is important. and I can group my event log into traces. Each one tells me the entire behavior of an instance of the process from start to end. Then there is another column designated that tells me what is the task that is being performed or that is being started or completed. And then I need a timestamp or anything else that allows me to order the events in some sort of total order. And there can be a lot of other data. And I'm not going to look into that at the moment. Already with these 3 columns and a bunch of those records, automated process discovery allows you to discover a model of the process. In the field of business process management, people generally use a notation known as BPMN, which is essentially, you can see it as a Petri net with syntactic sugar. Don't tell the people of BPM that I said that here today, okay? That is forbidden. But just between you and I is BPMN with syntactic sugar. This is a task, call it a transition. This is an AND split, meaning that I start 2 concurrent branches. This is an AND join, which means I synchronize the 2 concurrent branches, which is a transition with multiple incoming places. This is a choice. Think about it as a place where you can either take one branch or the other. And this is another choice. You can do this or you can do that. So this is parallelism, synchronization, and this is choice, and there can be merges. This same gateway can be used to merge like a place as well. There are many algorithms for doing automated process discovery of different levels of sophistication. Probably the simplest one is called the alpha algorithm. And what the alpha algorithm does is that it takes the traces, say I have a trace A, B, C, D, A, C, B, E, A, B, C, E, and it first starts looking at which tasks directly succeed each other in at least one trace. And it defines a direct success relation. For example, there is at least one observation where A comes immediately after B, at least one observation where B comes immediately after C, etc. Using these, it derives a causality relation that says that A occurs before B, C occurs before E, and so on. And from this sort of causality relation, we can derive some concurrency relation. If we observe that sometimes A comes before B and sometimes the other way around, like we see the different interleavings of A, of B and C occurring, we will say that they are concurrent. So, incorporating into the alpha algorithm is a notion of a concurrency oracle. You have a set of traces, they are total orders, and it identifies which pairs of events are concurrent to each other. That notion of concurrency oracle is something I will be talking about a little bit later. And then everything that is neither in causality, meaning that it's not always the case that A comes before B, nor in parallel, it's mutually exclusive. Right? It's either one is in the trace or the other is in the trace. So given a log, what the alpha algorithm does is that it derives a matrix of behavioral relations between every pair of task labels that appear in my log. Every event has a label, say that refers to a task, and I take all those labels, and the alpha algorithm essentially calculates a matrix where every cell will be annotated with one of three relations, causality, concurrency, or conflict. Given that intermediate representation, so this is basically the foundation of the algorithm, there's a number of rules, call them heuristics, that will tell me that, for example, if I have that A causes B and A causes C, and B and C are in parallel, I will generate this fragment of a process model. And by the way, it generates the workflow nets, Petri nets, not BPMN, but from workflow nets. There are some very nice methods that will allow you to go from free choice workflow nets to BPMN and vice versa. So it's pretty much isomorphic. And there's like 8 of these rules in the alpha algorithm, and with those rules you get a log and you transform it into this table, this matrix, and you discover the process models. It does have a lot of limitations, this alpha algorithm. There was a paper presented here 2 years ago by Eric Baduel on the alpha reconstructibility of workflow nets, which essentially characterizes very precisely when can a process model, what workflow net can be reconstructed from a log. You take a net, you simulate it, you get all its runs, and you try to apply the alpha algorithm. When do you basically get back what you expect? And it's pretty lossy. It only works with, well with a very regular, well-structured processes. There has been a lot of attempts at, within the same framework, to improve the technique. For example, by improving the concurrency oracle, so that, for example, some types of short loops, small loops, don't get confused with parallelism. That has led to alpha plus, alpha hash algorithm, same as C. C, alpha, same thing, right? But fundamentally, the problem is that in this table that we're seeing here, this table is fundamentally lossy. There's a lot of information in the log has been lost when I came here. So to keep some of this information, what some people do is that essentially, instead of writing the relation in that matrix, I will write the frequency about how often B comes after A, right? So I write a number, not just a relation, but a number that gives a weight to a certain relation. And with that, I can do better than alpha. And in practice, that leads to something called a heuristics miner, which for practical application has been shown to be a very good algorithm. There has been very extensive benchmarking done on this using real-life logs, synthetic logs, and this one is pretty solid, but obviously still has some shortcomings. So people have tried everything. Whenever you have a problem where you have to search, you have a process model, and some process models are better than others, then you can use genetic ants, everything you want, optimization. Some other field of research in automated process discovery has looked at using region theory to synthesize nets, or other Petri net synthesis techniques, coding the problem as an integer linear programming problem and solving it as if it was an optimization problem, because ultimately it is an optimization problem. Because when you have a log and you discover a model, you are looking several things in the model. You are looking at the model that you discover being as simple as possible. Simple means less number of nodes, but also less complex structure. So if you think about cyclomatic complexity or related notions, you want that to be minimized. But you also want to discover a model that parses the log. You don't want that some traces in the log are not parsed by the model anymore. So that's fitness, we call it fitness. You also kind of don't want that the model can generate traces that are not in the log. So you want it to be precise, we call that. However, we can differentiate here between two types of traces that the model can generate. There can be traces that the model can generate that are not in the log, but that by generalization one can think are part of the process that is being observed. And there are the others that, well, cannot be justified by generalization. So what the people in process mining have done is that they have defined metrics for this thing. Like we say, the model should not parse too much that is not in the log, but also something for generalization, which is that if I generate a trace that is not in the log, it has to be something that is implied by the log. And to define generalization, you can use a very typical trick in data mining, which is that you take your data set, in this case the log, and you split it into, let's say, 80%, 20%. You apply your algorithm, in this case the automated process discovery algorithm, with the 80%, and then you see if it parses the remaining 20%. Right? If it does, ideally it does, then you are happy. So it generalizes well, 100% of generalization. The fact that it does that means that it parses traces that were not in the log that was given as input, which means you lose in precision. So it's a bit of a balance between these two dimensions. But since we can reduce we can define metrics for how good a model is with respect to a log. We can use all sorts of optimization procedures to tackle this problem. Okay, so that's my overview of automated process discovery, and I guess that people experts in the field like will have disagreed with me to the point that he's looking for a pen to provide all his disagreements. There is
if you want, I disagree.
Yeah. So there is another problem related to that, which is conformance checking, and it's quite related to these dimensions of quality of discovered process model that I taught. In conformance checking, it's kind of easier. I give you a model, and I give you a log, and I just want to tell you if this log and this model kind of match each other, and if not, to what extent they do not match. Right. You can attack this problem by taking the traces and starting to replay them, just parse them. And whenever you see there's a problem, you keep a note. I had a problem when parsing this trace, or you can check that sometimes the model can do things that cannot be done in the log, and so on. Let's say the state-of-the-art, the technique for this problem is based on something called trace alignment. You can see the model as producing a set of traces conceptually. Like, for example, A, B, C, D, E will be a trace that this model can produce. And the log contains traces like A, B, B, C, E. And there are lots of traces here and lots of traces here. So you can say, I will find the trace in the log that, given a trace in the log and given a trace in the log, I'll try to match to the best trace in the model I can. The one that comes closest to matching it. And then I'll align them, which means I'll put them together and see what prefixes they share, and when I can do a move in the model that cannot be done in the log, I'll put some tau there. And similarly, when I can do a move in the log that cannot be done in the model, I'll put a tau there. And what I'm trying is to minimize these taus, these silent steps. I try to find the alignment that minimizes that. And if the number of taus I need is 0, then it's perfect conformance. If the more there are of these taus in the alignments, the worse you are. So that's for conformance checking, and this technique I have nothing against it. But when you have a real-life log and a real-life model, you will have tons of these little alignments, as I will show later. Given these alignments, by the way, you can actually define these two notions that we saw before: fitness, how well the log is capturing the model, how well the model parses the log, and precision, meaning how much more does the model have traces that cannot be observed in the log, that are not observed in the log. So you can define these two metrics, you can derive them from your conformance checking. The third problem that people in process mining deal with is, I call it deviance mining. I give you a set of traces. Every trace consists of a sequence of events, E1, E2, E3, En. And by the way, these traces might have data payloads inside. For example, a purchase order has a number of attributes. So when you say, when event create purchase order happens, there's a payload behind that carries all the data attributes of that. I have a lot of these traces, and I am given as input a labeling function. Something that tells me that some traces are good, given a trace, tells me is it good or is it bad. Right? And this good or bad might be determined by not being known. You cannot derive it from the trace. It might be, for example, was the customer happy or did the customer complain? Bad means there was a complaint after the case finished. Good means there was no complaint. The customer was happy. Or the case was on time or not on time with respect to some temporal threshold. And what you want is to, you have this function, but it's a post-mortem function, that is not based on the events that are occurring in the trace, and you want to reverse engineer a function, your own labeling function, that approximates as close as possible this function that was given magically to you. So users label the traces as this is good, this is good, this is good, this is bad, this is bad, this is bad, and you want to derive an analytical function that approximates the user's opinion. And you want this to be as accurate as possible in the sense of classification accuracy, precision and recall, but you also want this function to be explainable. It's a rule mining problem. You want to find a set of rules that explain when are customers satisfied and when they are not satisfied. Or what makes that, how can you characterize the processes that are executed in Estonia versus the one that are executed in Belgium? What's the difference between them? So this is like a rule mining problem where you have an accuracy part and you have an explainability part in what you are discovering. This problem is, can be handled in at least two ways if you look at the literature. One is like, I know how to discover models from logs, don't I? So I have two logs, I can discover two models. And I can then put them next to each other and compare them. And I can see, for example, that in the bad cases, I have some transitions that do not exist in the good cases. Right. So this is how practitioners approach it. So this is a paper from the practitioner's perspective. But obviously it has its limitations, because what I didn't say about automated process discovery is that it works, but sometimes produces these or worse than these, a bunch of spaghetti. And obviously here, if I had to explain what's the difference between the good cases and the bad cases, I'll be a little bit in trouble, right? Now, the people in data mining have been studying these discriminative mining problems for a while, and particularly there's a whole field called sequence classification, where you give sequences labeled, these are good sequences and these are bad sequences, and it can be sequences of events, possibly with payloads, and they will find features and rules based on these features that differentiate between the good ones and the bad ones. For example, this is a case study of some bank in China where they apply sequence mining to a log consisting of sequences, and they found that when event open occurs at least 2 times, then the trace is anomalous. But when event close occurs 1 and reject occurs 1 and reopen does not occur, then it's anomalous. So with respect to a certain notion of a certain function that tells you this is a good trace, normal trace, or an anomalous trace. So that's pretty much the state of the art as part of deviance mining goes. If you have a deviance mining problem in process mining, you just run sequence classification techniques and they come up with a bunch of rules that tells you when the case is good and when the case is bad. And typically this involves a combination of sequence mining techniques where you extract association rules in essence combined with decision trees. Okay, so that's my tour of the state of the art of process mining in 20 minutes. That's 25. And what strikes me the most about this is that every time there is a problem, there is a solution. Sounds good, but there is a different solution with very different foundations. So automated process discovery tackled by means of behavioral relations or by means of theory of regions, etc. Conformance checking tackled by means of replay or by means of alignments. Deviance mining tackled by means of delta analysis of models, comparing models, or by means of sequence classification, and the list goes on. So that brings me to my proposition, which is that we can see all the problems in process mining in terms of a small set of primitive operations using a unified formalism, and I will try to convince you that that formalism is event structures. Why do I think this is the case? Is because my main observation is that the reason why these things are different is because what we don't have is that in process mining we deal with models and we deal with logs, and we treat them as different artifacts. So if you have a problem of comparing a log versus a log, you will use sequence classification techniques. And if you have a problem of comparing a model versus a log, then you use something in between, which would be these trace alignments. And if you are reasoning more in terms of the model, like in automated process discovery, then you use behavioral relations or theory of regions. And what I think is that event structures allow us to capture these and these in the same framework. And then by means of a few operational event structures, we can characterize these different problems that have been studied separately in the field of process mining. Let me just briefly introduce what an event structure is. It's the simple type of concurrency model, I believe, a small beast, where it's a graph, and there are events labeled, and there are three relations. Causality, like for example here I'm saying that B occurs after A is a cause of B. So this occurrence of B must be preceded by A, and causality is transitive, but for to keep it simple, I do not show the causal dependencies, I only show the transitive closure of the causality relation. The second type of relation is conflict, meaning that if this event C occurs in this configuration, in this state, then B can no longer occur, and vice versa. And the third relation is concurrency. And concurrency is not shown explicitly, simply if there is no link, there is no relation shown between two events, then they are concurrent. They are concurrent in any order. So this process in this event structure here denotes one run only, where A is performed, then in parallel I have B and C on the one hand, with a causality relation between them, and B followed by B. In this one, I have first A, D which is preceded by A, B which is preceded by A, and C which is preceded by A, but C and B are in conflict. If C occurs, B does not occur. Now in event structure there is no notion of a join place. So if I want to say that after C, E can occur, I use one copy of E. And if I want to say that after B, E occurs, I use another copy of E. So these are two different futures. So as soon as you have an source split, which is an exclusive choice, you don't merge it, you keep separate copies. There is a very tight relation between Petri and event structure by means of the theory of unfoldings. If I have a Petri net, I can unfold it into a branching process, essentially, by eliminating the joints, the places with multiple incoming arcs. So I untangle the Petri net. In the case of an acyclic Petri net, you can do that until the end, and you get an occurrence net. And from that, this thing you can, every node in this unfolding becomes a node in the event structure, and you can trivially derive the relationship between every pair of labels. That gives you the event structure for this one, which in this case is A followed by B and C, choice between B and C, followed by choice between D and C in both cases, or between B and D. In one case is between B and C, and the other one is between C and D, and the other one is between B and D, followed by D at the end in all cases. So you see that D appears multiple times, each corresponds to a different unfolding of a different branch in the unfolding of this process. I can also do unfoldings of cyclic nets. I mean, if you keep repeating this, a Petri net with cycle gives you an infinite event structure, but you can stop in the middle. It's very well known. That's called a complete prefix unfolding. There's a whole theory for that. And in a complete prefix unfolding, it's like an unfolding. But when you get to a place that corresponds to a state you have already seen before, you do like a backward jumps. And you can also do sideways jumps and forward jumps as well. There are many ways you can do an unfolding. In our work, we sometimes prefer another longer unfolding that captures all the causes of an event. So here, it's not obvious that, for example, B is a cause of C in some branches of the process. But if we keep unfolding it, we get a larger unfolding where it becomes evident that there is a branch of the process where B is a cause of C, B is a cause of C, and I can even see that BC, BC are repeated, so somehow I can see the body of the cycles in this unfolding. You can define lots of unfoldings by just changing the condition where you stop unfolding. Given these two event structures, one of the beauty of event structures is that behavioral equivalence, in the sense of opposite equivalence, is the same as isomorphism of the event structures. And there are very nice algorithms for testing isomorphism. And when two things don't match, there are very nice algorithms for calculating the graph distance of between these two graphs. So I can map behavioral equivalence problems, I can map them to isomorphism testing problems or graph distance calculation problems. So if I have two process models, I can calculate their event structures, and I can compare them and check whether they are equivalent, and if not, why they are not equivalent, by essentially doing some graph distance, error correcting graph matching. And we have done that. We have defined a notion of a partially synchronized product, where you will start matching the initial events, the source events in the event structure, and then trying to match, to do as many moves as you can forward. Like here, both of these systems can do A, B after A, and D after A, but they differ because this system can do C after A, whereas this one cannot. So we note that one of the two event structures cannot do a move by means of some operation left hide in this case, because we're hiding on the second one. And we error correct and go back to a configuration where we can continue the synchronized product of these two event structures. We call that a partially synchronized product of two event structures. This is a fragment of it. There are some branches I am not showing here in this partially synchronized event structure. And this actually is telling me basically, if I summarize it, that after A in one, I can always do BD in both cases, but in one case I can also do C in conflict with B, and in the other event structure I cannot. We have defined a set of around 8 rules that when you are in a given configuration in these partially synchronized products between two event structures, based on what you are hiding in one and what you are keeping in the other event structure, we can verbalize the difference that is observed in that configuration of the event structure. So, for example, I can say that in this case, invariant 1, A precedes B. In one event structure, A precedes B, whereas in the other one, these are mutually exclusive. So I can generate from this mismatch here, I can generate something that tells me in this event structure, C and B are mutually exclusive, event C and B are mutually exclusive, while in this other event structure, in this configuration, B precedes C, as you can see it here. This precedes that. So I can take two event structures, I can generate a set of different statements, which I can represent in natural language, or I can represent visually. And we have developed a tool called BPDIF that you can find online, that you give him two BPMN process model, it translates into Petri, it computes the unfolding, this causality preserving unfolding, because that allows us to reason about differences in repetition, when is something repeated in one model and not in the other, and then it spits out a set of difference in the forms of statements. Every difference has a verbalization that refers to the task in the process, and we can also visually show exactly in the models where these two models differ. With colors, we can even show exactly what type of difference there are. So what we have here is a spot process model or a PetriNet workflow net comparison method that is based on event structure, that computes the event structure and exploits this property that behavioral equivalence for event structures is the same as isomorphism to derive a diagnostics of the differences between two event structures. In this case, between two models. And I reckon that this is a central component of how we can rebuild the process mining discipline on unified foundations. I'm going to show you how event structures can be used to tackle the problem of deviance mining, conformance checking, and process discovery. I presented them in this order, but in process discovery, conformance checking, and deviance mining, I'm now taking them in the reverse order because it's easier to start with the logs, and then we move to the models where we have these problems of fitness and simplicity and so on, which is a bit more complicated. So, the first thing is like, given an event log, we can compute an event structure that captures that log pretty much losslessly. The trick is the following. We first apply a concurrency oracle that looks at the logs and the interleavings that are found there, and that tells you which pairs of labels are independent, meaning are in a concurrency relation. There are lots of those oracles that have been defined in the past 20 years, roughly, of different levels of sophistication. They are not perfect, but in practical application, they have shown to work pretty well. So they find which tasks are in parallel and which ones are not. Once we have the parallel relation, I can take these traces that only differ because of the interleavings and merge them into runs, partially ordered traces. So I can get from this log a bunch of runs. You can see the process as being a big XOR between these runs, right? And here's the idea. The idea came to us because in the field of stream indexing, if you have a set of words, they use something called a suffix tree to index them. They take all the common suffixes and they represent them only once. So then I thought, why not we represent a log as a suffix tree? And one of my colleagues says, you are stupid. There is simpler than that. We can use event structures. And then we can do prefix compression instead of suffix compression. Because what the event structure will do is that if two runs share the same prefix, they will be this prefix will be represented only once in the event structure. Suffixes are represented multiple times, but the prefix only once. So we defined an operation called run merging, which takes these different runs, and as soon as there is a common prefix, in this case A is a prefix of everybody, it will capture it only once, and when they start diverging, like here in one case we have BC, in another one B, and the other one C, then it will start trying to capture the differences by using now the behavioral relations in an event structure. So out of this set of runs, I can derive that. I can do better. I know the frequencies of the runs. This run occurs 5 times in the logs, 2 times in the logs, 3 times in the logs. I can propagate these frequencies to the nodes in the event structure. And I can then prove that from this event structure, I can generate exactly the set of runs I had initially. So I can go from a set of runs to an event structure, prime event structure, and from the prime event structure back to exactly the same set of runs. And if my concurrency oracle is perfect, then I can then go, in principle, I can go back to the traces as well. So I have, in that case, an event structure that is completely isomorphic to the log. Right. There's a bijection between the two. So we then can take a log, turn it into an event structure. I can take another log, turn it into an event structure. And I have this operation for comparing event structures I talked about before. I can calculate their synchronized product. And from this synchronized product, I can find what are the differences between two logs. Which means I have pretty much a solution to the problem of deviance mining. Two logs explaining the differences. Now, people are doing deviance mining with sequence mining, so how have I advanced humanity by doing that? We have not, but at least we have not made life worse. I take these two examples here. These some real-life hospital logs, 448 cases and 363 cases, positives and negatives, and I can derive with this technique 48 statements of more or less this form, that in one, these two tasks are exclusive, in the other ones they are not. If I apply state-of-the-art sequence classification techniques, I get not 48 statements, but more than twice the amount of statements, if that matters. And these statements are of the form like, if a task occurs more than 7.5 times, oh my god, then it is of type 1, which means negative. If it occurs less than 7.5 times and more than 1.5, it is an L2. So I will argue our statements are not necessarily less intuitive than these ones, and we produce many less. More importantly, we can even produce only a subset of them, because we are traversing the event structures from the beginning, so we can tell you what are the first 10 differences and stop there. We can be incremental, right? Something that sequence classification techniques are not necessarily able to do. So I can take the same idea, similar idea, and tackle the problem of conformance checking. Now I have a model and I have a log. And I want to compare the model and the log. So I have this model here. A parallel B and C sequence and B. And I have a log, and they differ. You can see that here B is not followed by C roughly. But instead C and B are exclusive. This is the then using the unfoldings, I can generate from this model an event structure, which is this one. We have seen it before. And from this log, using this log run merger, I can derive this event structure, which tells me that A is followed by B and D in parallel, or C, B is exclusive with C, C is followed by E, B and D together are followed by E. So basically, this is the model corresponding to that log, and you can see that here B is followed by C, and here they are exclusive. And with our, now I have two event structures, one from the model and one from the log, and I can apply the same operation for comparing event structure by calculating their synchronized, partially synchronized product. And from that, I can derive a set of statements that tells me this model is not, this log does not conform to this model because in the model that C and B are in conflict, whereas in the log, B precedes C. And I can give a number of statements and that's my output for conformance checking. How have I made the humanity better? Again, I have not, but I would argue I have not made it worse. In trace alignment, which is state-of-the-art technique for conformance checking, if I have this model that generates this log, these traces, and I am giving, no, sorry, this is the log, this is the model. This model generates these traces. What trace alignment will do is that for every trace here, you find the closest trace there, and it will build me an alignment. And in this example, which is relatively simple, I get 3 alignments, and this is effectively what trace alignment gives me back. If I have a more complex model and a more complex log, I get a linearly larger number of statements. And all that this is telling me is that there is some aligned trace between the model and the log where after A you skip B. And here it's telling me that after D I sometimes skip C. And sometimes after D I skip B. And it keeps telling me this forever. And I have to guess that that means that in one model B follows C and in another one B and C are exclusive. So I think that we kind of improve a little bit in terms of the level of abstraction at which we give the diagnostics for conformance checking with respect to state-of-the-art techniques. And the biggest problem, which is automated process discovery, I reckon it can be done. However, we have not done it, and nobody has done it. But our hypothesis is that you can tackle this problem by going from a log to an event structure. We know how to do that. From an event structure, there are known techniques for synthesizing a net. So I can synthesize a net. Now, this net is going to have a lot of duplication because the event structure is unfolded, so it has a lot of duplication. So what I propose is that we can get rid of that duplication and generalize at the same time using probably one single operator. And that is a folding operator that will fold 2 occurrences of the same event, in this case D and D, into a single transition, like this, like transition fusion. If these 2 things are such that the future of one contains the other. This is the future of D, and this is the future of this D. The future of D is E and F. The future of D is E. EF contains E, roughly. So I can then fuse them into a single. We can see here that kind of generalizes in the sense that now I can produce, what can I produce that I couldn't before? A, B, C, A, B, D, followed by F, which was not in the law. So I'm generalizing and creating something that is not in the law. What's beautiful is that the same operation can generalize cycles. Because in an event structure, when you unfold it, when it's unfolded, which is the case of an event structure that you extract from a law, you will have AB, AB. So you can merge the two edits. Why? Because the future of one contains the future of the other by definition of the cycle. And that should basically allow you to not only synthesize readable, simple nets from logs, but also do something I would call control the generalization. You generalize only in some cases and not in others. Right. So that's what I call process mining reloaded, is that the whole operations in process mining can be reduced to basically 4 operations on event structures. I started by talking about process model comparison. I take one process, I take another process, I can unfold them and compare them. That's not traditional process mining, this is a process modeling problem, but just mention it. If I have a log, I can merge the runs in the log into an event structure. I can then tackle the problem of deviance mining by merging 2 logs into event structures, by folding into event structures, and then comparing them. So I have this merge operation and the compare operation, and I can tackle the problem of deviance mining by combining these 2 operations. I can tackle the problem of conformance checking by taking a model, unfolding it into an event structure, taking a log, unfolding, merging it into an event structure, and comparing the 2 event structures using the same compare operator. And I can tackle the problem of automated process discovery by taking a log, merging the traces in the log into an event structure, and synthesizing a net from there, and then folding the transitions in the net until I get the process model that strikes the trade-off I want to strike between these 4 dimensions. It all sounds very beautiful, as everything sounds at the beginning, before you start doing the thing. And we have started to test this for conformance checking. And some people say, oh, it won't scale. Well, it does scale if you consider that processing a real-life log in a few seconds is scalable. If you want sub-second times, millisecond times, it probably will be hard with these techniques. But if you are in a scenario where you are willing to tolerate a little bit more than sub-second times, then this can actually work pretty well. But there are a number of stumbling blocks, bumps in the road ahead. One of them is that when we synthesize an event structure from a log, we rely on this notion of a concurrency oracle, something that inspects the log and tells me these 2 events are in parallel, are independent. There are lots of concurrency oracles in the literature. Unfortunately, we still need a few more because they are far from perfect. But I'm sure the community here will manage to solve the problem by the next Petri conference, which is great. This notion of folding and fusing transitions for the purpose of automated process discovery is an open problem. I just think it's solvable, but somebody has to still do it. And then we have revisited the theory of process mining without considering the payloads in the events. Obviously, in real life, the payloads in the events are very important. They carry a lot of information, and we need to incorporate that into this vision of process mining and reload. And that's it for me.
Okay. Let's thank Tom.